In the clear southern sky above the Atacama Desert, the easel-shaped constellation of Pictor lurks between the bright star Canopus and the vague smudge of the large Magellanic Cloud. Among the brighter pinpricks that define it, a faint, cool, reddish star flickers at the very edge of visibility. But its relative dimness is no obstacle to the telescopes on the ground and in space, now trained on its feeble light. Some 200,000 kilometers above the Earth's surface, the orbiting TESS telescope notices a strange, periodic flicker to the star's light. On Earth, we would assume such a twinkle to be caused by distortions in the planet's gassy atmosphere. But not so here in the vacuum of translunar space. Watching this star, now poetically named the TESS Object of Interest, TOI 270, the spacecraft sees periodic dimmings and counts 1, 2, 3 objects passing in front every 3, 6, and 12 days. They are exoplanets, members of an alien solar system 73 light-years away. These and thousands of other distant exoplanets are far too distant and too dimly illuminated to be photographed, but scientists nevertheless flex their astronomical muscles to discover all they can about this alien family. The sizes of the dip in starlight, as measured by the TESS spacecraft, correspond to the size of the transiting planets. And by precisely measuring the gravitational wobble of the star itself as the planets swing around it, astronomers can accurately estimate the mass of each orbiting body. Size and mass together give density, and with it a good idea of the exoplanet's composition. Thus, from the light of the star alone, we can learn much about its invisible companions. Indeed, we have characterized several thousand exoplanets in this way. But the exoplanet family around TOI 270 presents something of a mystery. One planet, closest to the star, is very much like Earth in density, and only a little larger. But the other two siblings seem to be of a different breed. They are more than twice the diameter of Earth, but they aren't as heavy as we'd expect them to be, if they were made mostly of rock. Neither are they light enough to be made mostly of gas. There must be something else at play in the planetary mix. These are not the only mysterious lightweight planets out there either. Among the 2,500 exoplanets detected by 2018, almost 2/3 of them had a density somewhere between that of rock and gas. Looking to our own planetary neighbours for inspiration, astronomers have suggested that these mid-size mysteries could be miniature Neptunes, containing a mixture of rock, gas, and heavier icy vapours like water and methane. But a far more tantalising prospect is that of rocky super-Earths covered completely in water. Vast global oceans completely covering the surface and feeding thick, humid atmospheres that maintain the planet's liquid skin. Such extensive superoceans could be havens for extraterrestrial life. And if this interpretation is correct, the thousands of planets like those around TOI 270 could be a promising new focus for the search for life forms beyond Earth. And close to home, we have hints of what a world of global oceans could look like. Europa, one of the 4 largest moons in orbit around Jupiter, is skinned with an icy crust. But layers of tortured scars and cracks in that crust betray the fluid nature of its interior. Less than 30 kilometers below the frigid surface, scientists believe there is a vast, global ocean 100 kilometers thick. A warm, rocky core pumps heat and minerals into that ocean. Enough, researchers believe, to sustain life. Yet, limited by its size and its exile into the cold outer solar system, Europa is a pale, icy imitation of the potential glories of a true ocean world. In picturing a warm, watery planet, we are left to our imagination and the vagaries of simulations with the scant data we have. If only we could travel back through time, then just 175 million years ago, or 1 billion years ago, or 3 billion years ago, the Earth itself could have lent structure to our imaginings. Because at several points in our planet's history, our world has been ruled by a single, global ocean. A superocean. Whose unique dynamics had the power to transform the Earth and life for millions of years. This video is sponsored by Magellan TV, the documentary streaming service. Magellan is essentially a Netflix for documentaries with over 3,000 quality works spanning loads of topics. They've been a great inspiration for us as we've plotted our journey through the Earth's history. An excellent resource to turn to help spark ideas. Their selection of science and Earth history documentaries in particular is great. And one example that teams well with this video is Life on Fire, a series that explores the remarkable ecosystems that can build up around Earth-shattering volcanoes. A cracking watch that gives great insight into the history of our globe. And you can now take advantage of an exclusive offer, 30% off an annual membership. This gives you an entire year for less than $3.50 a month, even if you've joined Magellan before and lapsed. You can simply click on the link in the description to claim your discounted membership today. Thanks. On the 21st of December 1872, a British Navy corvette floated out of Portsmouth, creaking and swaying on a falling tide with the wind rippling in its sail. Small warships like this one had seen action in the Napoleonic Wars, but this particular vessel was not bound for conflict. It had had its 17 guns removed and scientific equipment installed in their place. Laboratories equipped with microscopes, sample bottles, and chemicals filled the ship's interior. A specialist dredging platform had been constructed, and nearly 300 kilometers of hemp rope was coiled on board, in preparation for deep water operations. This was the HMS Challenger, the very first dedicated oceanographic ship, which set out to fill in the blank blue spaces in our maps of the seas. Of course, Challenger was not the first to explore our vast and mysterious oceans. Its voyage had been preceded by great expeditions by Columbus, Cook, and the countless unnamed natives of coastal lands, seeking to discover what lay just beyond the horizon. But the motivation for all of these maritime journeys had been, primarily, to discover more about the lands on the other side of the ocean, not the oceans themselves. The Challenger expedition of the late 19th century was really the first to set its sights away from the land, and instead pursue the mysteries of the deep. Probing the open ocean and the sea floor to learn how this gigantic portion of our planet really worked. For 3 years, the ship trawled Earth's many interconnected oceans, travelling the South Atlantic, the Indian Ocean, the Southern Sea and South Pacific, before returning to England in May 1876. The naturalists on board sampled the water, seafloor sediments, animals and plants, using trawlers, nets and scoops. The sounding ropes measured the depth of the sea floor as they travelled, revealing for the first time the shapes of the ocean basins, and discovering one of the deepest parts of the ocean in the Western Pacific. Plunging to a depth of more than 11.5 kilometres, this vast submarine abyss is now named the Challenger Deep, in honour of the little ship that found it. Challenger's discoveries were exciting, novel and revelatory, but they were by no means comprehensive. The tantalising morsels of data the expedition returned gave life to the brand new science of oceanography, which continues to make brand new discoveries to this day. As with so much of science, great advances are made during times of terrible conflict. And as opposing sides sought maritime advantage during World War II and the following Cold War, we learned more about our oceans than ever before. Today, our titanic oceans cover more than 70% of the Earth's surface. With an average depth of nearly 4 kilometres, the shallowest sea floor lies on the continental shelves next to most major landmasses, but then plunges down to the flat, abyssal plains that underlie each great ocean basin. And, at their opposing edges, these plains dip even deeper into narrow ocean trenches. The Challenger Deep, part of the Mariana Trench at the western edge of the Pacific Basin, is one such hellish crevasse. It is often said that we know more about the surface of the moon than we do about the depths of our ocean. This is in part true, and is little surprise given the clarity with which we can see our dry, airless natural satellite and the relative ease of visiting it. For the bottom of the oceans, it's a different story. Water may seem benign, pleasant and innocuous to our eyes, but when more than 1.3 billion cubic kilometres are pooled over the Earth's surface, it becomes one of the most potent barriers to scientific study we know of. Sunlight can only penetrate the top 200 metres or so, leaving 95% of the abyssal depths in utter blackness. We have no hope of seeing the ocean floor from the surface. Were we to travel to these ocean plains, to traverse them and map them as ancient cartographers once did the land, we would be faced with another crippling barrier. 4 kilometres of water above the would-be explorer exert a pressure some 400 times higher than at sea level. Enough to crush the air out of their lungs and buckle all but the strongest pressurized craft. Combined with the oppressive blackness and freezing temperatures, this is an environment more hostile than even the far-flung depths of space. And so, modern oceanographers must use other tools to understand this alien world on our own planet. Instead of seeing with light, they take their inspiration from the natural world and scan the ocean floor with sound. Like hunting sperm whales and bats who emit ultrasonic pulses and build a picture from the returning echoes, ships on the surface of the ocean scan the abyssal depths with sonar and use the echoes to map the shape of the seafloor beneath their keels. Sonar and gravity readings have helped us map all our ocean basins, but only to a very coarse level. At just 5-kilometer resolution, objects as large as Central Park or the entirety of Gibraltar could be missed. Higher resolution scans on a 100-meter scale are still in progress, but only about a fifth of the oceans have been imaged at this level. And new features are being discovered all the time. In 2009, a 4-kilometer wide crater was discovered on the Atlantic sea floor. Prior to the higher resolution imagery, we had no idea it was even there. Since we first dipped our toes into oceanography, some 150 years ago, our knowledge of the seas has grown hugely. The light we have shone into our mysterious oceans has helped to reveal their role in our planet's endless geological cycle. Reading the shape of the ocean floor helps us build a picture of those oceans' evolution over unimaginable eons. And so, although they may seem quiet, static and passive throughout our fleeting lives, in reality, the ocean depths are constantly transforming, reshaping themselves and the character of the entire planet in turn. Edward Seuss enjoyed his academic life in Vienna. This elegant city, with all the coffee, chocolate and home comforts a 19th century man could hope for, was also within easy reach of the geological marvels that so fascinated Seuss. In just a few days, by carriage and horse, he could ascend into the towering alpine peaks, or descend to the Mediterranean coast, comparing and cataloguing the rocks he found along the way. As professor of geology at the University of Vienna, he considered it his responsibility to know all there was to know about his corner of the world. And he matched his diligent observations with carefully considered speculation on how things came to be. Seeing structures on the high mountain peaks that seemed to correspond to submarine processes, Seuss suggested that the Alps had indeed formed at the bottom of a now-lost ocean. His hypothesis of how they came to be raised nearly 5 kilometers above sea level was, unfortunately, rooted in the accepted views of the time. That the Earth was cooling after its fiery formation, contracting and therefore crumpling the surface. Rocks that had once smoothly lain at the bottom of the ocean were buckled upwards, shaping mountain ranges with the remnants of seafloor sediments at their tops. More than 100 years on, with information gleaned from oceanography and global geology, we know now that this so-called contractionism theory is unfounded. Rather, our ocean basins and land surfaces have been shaped by the constant cycles of plate tectonics over billions of years. And yet, Seuss was correct in his assertion of a long-lost ocean, whose remnants are now perched at the top of the Alps. This ancient ocean he named TESS, after the Greek sea goddess who was wife to Oceanus. Alongside Tethys, Seuss identified another ancient ocean, of greater, more magnificent extent. He named it Panthalassa, Greek for all sea. Long before geology entertained the concept of continental drift or plate tectonics, Edward Seuss imagined a time when the oceans were combined into one great all-sea. A vast superocean that covered much of the planet. Seuss couldn't have known how right his speculation had been. Tracing the ancient history of our oceans is not a straightforward task. While the remnants of continental crust tend to stick around, buoyant and resistant in the face of tectonic clashes, it is invariably the luckless oceanic crust that meets its end. Trace chemical evidence from the planet's first few million years tell us that water was delivered to the planet in such a quantity to create great, pooling oceans. And we also know that plate tectonics, after a stumbling start, eventually began to create continental and oceanic crust, with distinct chemical and geological characteristics. But the actual geological record of oceanic crust, the dense basaltic slabs that underlie our abyssal plains, is shockingly shallow. The oldest parts of the ocean floor today are a mere 200 million years old. New data from a few isolated basins on the eastern Mediterranean suggest that the sea floor here could be almost 340 million years old, a remnant of Seuss's Tethys Ocean. Yet, either way, compared to the roughly 3.5 billion year history of plate tectonics, a few hundred million years is a figurative drop in the ocean. 95% of ocean crust history has been lost forever. How then are we to recreate the history and dynamics of ancient superoceans? Like the oceanographers who thought laterally to image the sea floor, geologists must use tools and proxies to reconstruct the echoes of these long-lost seas. Some of the biggest clues that can reveal not only the past existence of an ocean basin, but also the dynamics of its demise, are what geologists call allochthonous terrains. Even though old, cold, dense oceanic crust may be sacrificed to the mantle in plate tectonic clashes, a memory of it remains in the unique rock formations that grew on its surface throughout its life. Just as a ship or a whale that drifts into the ocean will accumulate barnacle hitchhikers over the years, so the ocean slabs will accumulate geological hitchhikers. Mantle plumes or ancient subduction zones will punch through the thin oceanic slabs below, building cone-shaped volcanic islands like those of Hawaii or the Ryukyu Islands south of Japan. Where the volcanic blisters grow close to the ocean's surface, their slopes are colonized by light-loving life. Coral reefs grow and build circular atolls that persist even as the volcano erodes away. The impassive persistence of plate tectonics cares little for these geological barnacles. The ocean slab continues to slide, pushed from one end and dragged under from the other, until the new-made islands teeter on the edge of the subduction zone itself. The ocean slab cannot escape its fate, but often these new masses of rock are simply too large to slide under the abutting plate. Instead, they are scraped off at the boundary to pile up among the contorted wedge of sediment that once blanketed the sea floor. These are the allochthonous terrains. Entire masses of rock that formed in one location were transported by plate tectonics and unceremoniously rammed into one another. Because of the chaotic nature of their assembly, these jumbled and sacked remnants are not easy to interpret. But information contained within the ancient coral atolls or the magnetic compasses from volcanic rocks can help to build a picture of the conveyor that brought them there. Another creative approach to reconstructing past oceanic basins extends the science of sonar to surprising depths. Sending sound waves through the fluid ocean can produce an echo that builds a picture of the sea floor beyond our sight. Now, geologists are sending seismic waves, merely another kind of vibration, through the upper layers of the Earth to build a picture of the structures in the upper mantle. When oceanic crust is subducted into the mantle, we find that it doesn't completely melt away. Rather, it snaps and slides downwards, slowly through the semi-solid rock, stacking up at the boundary between upper and lower mantle, where density changes stop it sinking further. By finding these stacks of ocean slabs 600 kilometers beneath the ocean floor, we can begin to rewind the tectonic conveyor and rebuild ocean layers that are hundreds of millions of years old. The murky oceanic history that these clues reveal is one of remarkable repetition. It seems that ocean basins tend to open and close time and time again along the same suture zones. The once separated continental masses converge on one another until the last shreds of the ancient ocean are consumed, leaving its crumpled echoes smashed into the ugly scar. A scar that will open up again all too easily when the tectonic tide turns again. In this way, our modern Atlantic is at least a second generation of ocean, preceded by the Iapetus between 600 and 400 million years ago. Of course, our greatest tool in understanding the evolution of ancient oceans is in the remnants of ancient continents. Ever since our water was delivered not long after the Earth's formation, geologists do not believe that the total volume of the oceans has changed. So, our abundant, if fragmentary, remnants of ancient continents and supercontinents give us indirect information about the oceans that surrounded them. When continents were dispersed, we can deduce ancient oceans that separated them. And when supercontinents assembled, the remaining 70% of the globe must have been covered by a single, vast superocean. The ages of the superoceans therefore correspond with the ages of supercontinents. And although understudied compared to their charismatic continental counterparts, they have, nevertheless, been christened with speculative names. And so, Edward Seuss titled The Last Great Superocean. Panthalassa was the all-sea that surrounded the supercontinent of Pangaea during its 150 million year tenure, throughout the Carboniferous, Permian, Triassic, and early Jurassic. Prior to Pangaea, the supercontinent Rodinia saw all land masses combined into one for several hundred million years during the late Proterozoic. But the planet was dominated by its superocean, Mirovia. Since living things had not yet colonized the land, this gigantic, singular sea connected all of life on the planet. As the history of supercontinents becomes less clear in the distant past, so too do the assumed superoceans that girdled them. Some paleogeographers suggest the supercontinent of Kenorland reigned about 2.5 billion years ago, and give a name to its companion superocean, Lerova. But with few geological proxies to characterize either land or sea so ancient, both Kenorland and Lerova remain speculation for now. So, we know that at various points in our Earth's history, the surface has transformed. there have been times of continental separation and continental collision. Similarly, there have been times like now, when the oceans are fragmented by land, and times when the vast majority of the surface has been united in a vast, singular ocean. Geology can help us reconstruct the history of these superoceans, but we must look again to oceanography to appreciate how these monstrous seas shaped the planet. On the Hawaiian island of Kauai, Mount Waiolioli rises a modest 1,500 meters above the turbulent surface of the Pacific. But from the summit, it is almost never possible to see the waters below. The smooth volcanic peak is almost permanently shrouded in thick cloud. This lonely mountain, nearly 4,000 kilometers from the nearest continent, is one of the wettest places on Earth. Standing alone in the center of the largest ocean on Earth today, it snags every passing cloud, precipitating a deluge onto its steep volcanic slopes. Nearly 10 meters of rain falls here every year. It is not difficult to imagine an island like Kauai existing some billion years ago, in an ancient superocean like Mirovia. This hemisphere-spanning ocean would have resembled the Pacific in many ways. It would be composed of several immense oceanic plates, each committed to their individual route across the globe, driven by convection currents and the forces of their own momentum. They grow as new material is added at mid-ocean ridges. But creation is all but balanced by destruction. Hundreds or thousands of kilometers away, at subduction zones, where plates meet, be they ocean and continent or ocean to ocean, the clash ultimately sends one slab plunging into the mantle, restoring the balance on the surface. Mantle plumes rise from the depths of the planet to push through the centers of these wandering plates, creating island chains, like Hawaii and the Emperor Seamounts, that preserve a trace of the plate motions as the crust moves over the hotspot. The geological processes are easy to visualize, but in a world ruled by one ocean, conditions at the surface become much more unfamiliar. Take, for example, the tides. On Earth today, tidal ranges vary massively around the planet as a curious consequence of resonation between water flowing in and out of individual ocean basins. In some places, high and low tides can be separated by as much as 15 meters. Yet, in a single superocean, these tidal resonances are diminished. As the planet turns, the mound of water pulled outwards by the moon's gravity can travel around the globe unhindered, and supercontinental shorelines are unlikely to see a tidal range more than about 1 meter in height. And for Rodinia, this equated to a globally small intertidal habitat, perhaps delaying the colonization of the continental fringes by Proterozoic life. The absence of any major barriers within a near-global ocean also has profound implications for the movement of air and water currents across the planet. Today, our oceans circulate via unseen currents that distribute heat from the sun-soaked tropics to the ice-covered poles. But this circulation is also shaped by the positions of continents. Cool, deep waters flowing north along the east coast of Africa are stopped in their tracks by the Indian subcontinent and are forced back south. The eastward flowing North Atlantic Gulf Stream is diverted north as it hits the European mainland. Weaving between continents, the ocean currents tie the seas together in a complex oceanic conveyor. It takes 1,000 years for water to complete its tour. But in a single, simple superocean, there are no obstacles to deflect and divert the currents. We see a hint of such circulation around Antarctica today. The newly defined Southern Ocean is an uninterrupted channel of water defined by a single immense circular current, chasing its own tail like the mythical Ouroboros, and moving 130 million cubic meters of icy water every second. Sailors know this treacherous stretch of ocean as the Shrieking 60s. Thanks to the high winds and towering waves that dominate the zonal circulation at 60 degrees south. And like the Southern Ocean writ large, superocean circulation is simple, devolving into two immense circular currents called gyres that dominate the north and south hemispheres. The sun continually warms the tropical oceans near the equator, and this heat attempts to equilibrate, moving towards the poles. But the spinning globe diverts it from a straight flow, deflecting it to the right in the northern hemisphere and the left in the south. This happens in our modest oceans today, but in a worldwide superocean there is nothing to stand in the way of these gyres, flowing towards the west in the tropics and to the east in the polar latitudes. Such constancy creates very different conditions on opposite supercontinental shores. On the eastern shores of Mirovia, cold waters are transported from the poles and upswell from the ocean depths. These cool, fresh waters contain nutrients dredged from the sea floor, which feed immense algal blooms and the life forms that evolved to exploit them. On the Rhodinian west coast, a productive tropical paradise reigned. But the tropical oceans today are also the nurseries of some of the most powerful storms on Earth. Warm surface oceans evaporate and build into towering cyclones that track westwards, feeding and growing as they go. Over the 4,000 kilometers of the North Atlantic, yearly hurricanes develop and lay waste to the Caribbean and US East Coast. In a superocean dominated by this westward tropical flow, where storms can travel and grow for more than 20,000 kilometers uninterrupted, the seasonal cyclones have the potential to reach truly deadly intensities. The eastern Rhodinian seaboard would be razed and ravaged by howling winds, ferocious rainfall, and colossal storm surges. Even hardy marine microorganisms would find themselves battered and bruised by the force of this immense weather. Stromatolites are destroyed at a stroke, and the coastline is continually reshaped by floods, landslides, and cliff falls. This is a messy, turbulent coastline where only the hardiest, or most foolhardy, choose to eke out a living. There is evidence from the rock and fossil record that these superocean circulations occasionally bred an even more deadly peril. That of stagnation and asphyxiation. For periods of up to 10 million years, parts of the Panthalassa became rigidly stratified, with life-giving oxygen failing to reach the lower levels of the Great Ocean. Although oceanographers still aren't sure exactly how it came about, the implications are clear. Without enough oxygen throughout the water, ocean creatures died in their droves. We may be thankful that we aren't living through a tempestuous and occasionally strangling superoceanic age. And even though plate tectonics grinds ever on, growing the Atlantic and reconfiguring the Pacific, we won't see another superocean on Earth for 200 million years at least. Future projections of our continental shifts agree that a new supercontinental age is coming as our current continents crash and crumple to become Pangea Ultima. So, it follows that there will be a superocean to girdle this new, gigantic landmass. But there is some disagreement over how that superocean will be formed. Some predict that the Atlantic Ocean will eventually stop its eternal growth and begin to close, just as the Iapetus did before it. To redress the balance, the Pacific will grow ever larger, perhaps splitting into more plates to accelerate the pace of growth from a greater number of margins. Other projections see the Pacific doomed, as the Atlantic opens ever wider, squeezing the ring of fire ever tighter until it is little more than a compressed seam of long-lost volcanoes. Or perhaps both the Pacific and the Atlantic will be no more, and it will be the Indian and the Southern Oceans that expand to dominate the globe. However it happens, the resulting superocean will be a formidable sea for our descendants to cross. And so, an extraterrestrial ocean world may seem at first glance to be a haven for life beyond Earth. But that life must be uniquely equipped to survive on a planet ruled by wild water, wind, and weather. You've been watching the entire history of the Earth. Don't forget to like and subscribe and check out our partner channels, History of the Universe and Something Incredible. And we'll see you next time.